Chain rule helps you find the derivative of a composite function. So earlier we learned that when you have a function and you want to find the derivative of it, we can use something called the quick rule. So this quick rule lets us quickly say that this derivative, if we have f of x is equal to 3x squared, we can easily say that it's just 6x. This is just because we have the exponent multiplied by the coefficient and 1 minus the exponent, which leaves us with 6x. What the chain rule does is it helps us find the derivative of composite functions. Let's say we have the composite function f of g, and we want to find the derivative of it. The chain rule says that this derivative is equal to f prime of g is multiplied by g prime. An easier way to see it for me is in a different notation. F of g, when we're trying to find the derivative of f of g, we'll get that f prime of g multiplied by g prime. Another way to kind of say this is the derivative of the outside function of the composite function multiplied by the derivative of the inside function, with that inside function inside of when we have the derivative of just the outside function. When we've been learning the quick rule, we were actually also using the chain rule. So if we imagine x as another function, we would say that this is 6x multiplied by the derivative of this inside function, which is just x prime, and that's just 1, and it equals 6x. So we've actually always been using the chain rule in our quick rule, but now we get to see it using actual composite functions. So if we have y equals 3x plus 1 squared, and we want to find the derivative of this function, we have to first identify the outside function, or that f. This 2 will be our outside function, and our inside function, that g of the composite function, will be right here, this 3x plus 1. So our goal in this problem is to find the derivative of y. So what's y prime? So what we learned in the chain rule is that we have to take the derivative of the outside function. So the outside function is this something squared. And we learned in the quick rule that we could just bring down this 2. And we have 2 minus 1, which is just this 1. And what we have inside that's left inside is this g function inside of here. Because we're just taking the derivative of the outside function and leaving the g within it. But then we need to multiply the derivative of the g function itself on the inside. And that's just, when we take the quick rule, that's just 3. So we get that y prime is equal to, when we simplify it, 3 times 2 is 6, is just 6 multiplied by 3x plus 1. And that's our answer. Another example would be this problem. So we want to find the derivative y prime. And so what we're going to do is we first have to find our outside function and our inside function. Remember that we learned that when we have f of x and we want to find the derivative, if f of x is equal to e to the x, we'll say that the derivative of this is equal to e to the x. This outside function will be this e to the something power, and the inside function will be our g, which is what this x usually was, which is this huge long equation. We're actually going to make this a square because it makes it harder. So we'll have this inside function be our x, kind of like that, the g, the inside function. So our outside function is that e to the x value, which is, we can underline this part, and our inside function will be 5x squared plus 7x minus 13. So we're taking e to the power of some function, and we're going to treat the power as the inside function. So let's take the derivative of the outside first. So we'll say that the derivative of the outside is e to the, since it's the same, e to the x, and that x is just this 5x plus 7x minus 13. But this is a separate function, so we have to take the derivative of this separate function, the inside function, which is this g. And that derivative, using the quick rule, really simply is just 10x plus 7, right? And we can't really simplify this, but you can write it kind of nicely in this way. So 10x plus 7 multiplied by e to the 5x squared plus 7 x minus 13. Okay, so we'll just have this. This is our answer. But what if we have a really long composite function made up of multiple functions that are inside each other? And what actually is kind of interesting is that the chain rule for many functions actually follows the same pattern. So for example, if we have f of g of h and we want to find the derivative of that, it's just equal to f prime of g of h multiplied by g prime of h multiplied by h prime. Do you see that kind of pattern? We take just the first function multiplied by all the other functions inside, and then take the next function in line and we multiply by all the functions inside, and then we multiply it by all the functions and continue that pattern until we get to the last function, which we take the derivative of, and that's how we do the chain rule for many functions making up a composite function. So let's try an example of this. This has many functions within it. We want to find the derivative of this in this equation. So what we're going to do is we're going to first have to identify all of the outside function to the inside function so we can apply the chain rule. So our outside function is this ln function because it's on the outside. And if you remember, this is just memory. If you have a function ln x, we should know that the f prime of x is equal to 1 over x, right? What's the next in line? So many people might make the mistake that the next in line is cosine, because linearly this looks like it's the next after ln, but actually it's the exponent 5. The reason is this cosine of 3x to the 4th is actually being taken to the power of 5. And then next after that is this cosine function. And then after that, the last function is this 3x to the power of 4 function. So what we're going to do is take the derivative of the outside function first. So we can say that the outside function is 1 over all the other functions within it, or cosine to the power of 5 multiplied by 3x to the power of 4. And we can multiply this again by the next one in line. So we have to multiply this again by this next one in line. So we bring it down like we know, the quick rule, and it's 5 multiplied by what's inside of it. It's this cosine function to the 3x, right? But wait, we can't forget something. When we take the derivative of something to the 5th, we have to remember that 5 minus 1 is the 4th power. So we still haven't had the 4th power. And then we're going to multiply it by the next one in line. The next one in line is the cosine. And we know that the cosine is, the derivative of cosine is negative sine. And that will be of the next function within it, which is 3x to the power of 4. And we're going to multiply it by the last function, the derivative of the last function in line. And that's that 3x to the power of 4. And we'll say that's 12x to the power of 3. And now we can solve it. We actually really need to simplify this one because it really changes the look of the answer. So if you look here, we have the cosine 5 of 3x to the power of 4 and cosine 4 3x to the power of 4. And this one will be on top of this one when we multiply these two terms out. So we can cancel each of them out and we'll be left with cosine 1 to the 3x over 4 on the bottom. So we can say this is 5 over cosine to the power of 1 multiplied by 3x to the power of 4. And then we can multiply it again by these two terms on the bottom. So we're just multiplying the terms on the bottom. And we actually still can simplify it further. We don't put this on the top of this so we can see it better. So that's kind of like 60x because negative 12 multiplied by 5 is negative 60. X to the power of 3 multiplied by sine of 3x to the power of 4 over the cosine of 3x to the power of 4. And this can be simplified even further to negative 60x cubed of tan of 3x to the power of 4. So that's really a big difference from this. So we really need to remember to simplify some of these chain rule problems. But do you see how we are able to use this huge composite function with many functions within it? We're able to take the chain rule and find the derivative of it. That's the really useful thing about the chain rule.